Hey all, and welcome to second semester. We're going to keep just going straight ahead, keep going with chapter 9, and then you'll have a quiz tomorrow on everything, including what we did last week with Euler's method and a nice review of separable equations. We're going to get started on one of our two growth models. We're going to do the exponential growth model today. And next week, we're going to look at the logarithmic growth model, which is much more complex. So it's nice to have a nice, easy one to lead in after a long weekend, which I hope you all enjoyed. So get yourself ready for notes, and we're going to get started. One quick thing, and you'll see this, of course, on the form and on Google Classroom, is that there is a presentation, and it's number 8 right here. Now, the exponential growth model is basically dp dt. So the change in population over time is a constant times the population. And k is a constant. As I said, it's the growth rate. And if you have memories maybe from pre-calculus, from one of your biology classes, you'll also remember that exponential growth is population in terms of time is p sub 0, the initial population, times e to the kt. And these two are the same idea. They are interchangeable, and it's really helpful to be able to recognize that these two operate in the same way. And I can show that to you, so we're going to quick justify this using separable equations. So justify the function p of t given the exponential growth model. So what we'll say is the exponential growth model, dp dt, is equal to kp. Since we want to separate those equations, get the p on one side, and then I'll just leave k dt, and then integrate now that our variables are lined up. So this is ln of p. Population's not going to be negative. The lowest population you can have is 0, so I'm not worried about that. Is equal to kt plus c. Remember, you only need 1 plus c. Now I'll raise everything to the e power. And here's something that you're definitely going to see as a trick on the AP test in all your calc classes that you have that involve exponential differential equations. We now have p on the left side is equal to e to the kt plus c. And the trick that you'll see a lot is that this is the same as e to the kt times e to the c. Because if we are adding exponents, they initially came from here. Now e to the c is just a constant, since c is a constant. And so you'll see it written as just another multiplier with a c like a coefficient. So what you'll actually often see on tests is c e to the kt. And these are the same. Now what we want to do is show that c is equal to the initial population. So I'm going to plug in 0 and say, oh, well, p of 0 is equal to c times e to the k times 0. So the initial population. Well, e to k times 0 is the same as e to the 0. E to the 0 is 1, and so therefore c is equal to the population at t equals 0. So p is equal to p sub 0 e to the kt. And that's how you get from the differential to the function. Now again, sometimes you can absolutely use calculus and it will be helpful in these things, but I often find it's easier to just use the population model that you remember from previous classes. You just have to recognize when you use it. So a question on the AP or in a textbook or in another class might say, assuming that the rate of growth is proportional to the population size. This means it is that exponential model, because remember, proportional is x is equal to ky. So in this case, the rate of growth, dp dt, is equal to k times population size. So whenever you see that, that just means, oh, gotta use my exponential growth model. and that means that I can use my P is equal to initial populations times e to the kt. And so in this case, it says that the population was 165 million individuals in 1990 and 175 million in 2000. So find the relative growth rate. What I would do here is I'm going to jump immediately to using that function from previous classes because I find that it's just often easier. So here I'm going to say, well, the population is now 175. The earliest one we know is 165, e to the kt. We're going from 1990 to 2000, so that means t is actually equal to 10 because it's about the amount of time that has passed. And since we're looking for growth rate, that means that we want to find k. What I would start with is dividing by 165 and then taking the log. So ln of 175 over 165 is equal to ln of e to the k times 10, so that cancels out and just leaves us with 10k. Use your calculator here and you find that k is equal to 0.005, and I'm just going to give one more data point, 59. Now in this case, I'm just going to save this in my calculator as an answer so that I can plug it in and be more effective for what I'm solving. So write an expression for the population size. So I'm just going to use that original equation, 165. You can write out 165 million, or you can just use million individuals as your unit, which is what I will do. 0.0059t, using my answer from part A. Now for C, find the population in 2010. What this means is that t is equal to 20, since that's years past 1990, years from our initial population that we were given. So I want to then find P of 20, which is 165 times e to the 0.0059 times 20. And this is where I'm just going to have saved this in my calculator. So what I'm actually going to type in is 165 times e to the, using the answer key, times 20 like this, so that I don't have any accidental rounding errors. And I end up with 186. And since I used 165 as my initial, that means it's 186 million individuals. And there's obviously more more figures from there. I'm rounding individuals. Now D, find what year the population reaches 200 million individuals. So here we're solving for T, but I'm still going to use that same function. The population's now 200. We start at 165, e to the 0.0059 t. Very similar to when I'm solving for k. Divide and then take the log. Equals 0.0059 t. Again, I'm going to use that as the answer, but just to keep myself from having any rounding errors, and I get 32.694. Now this doesn't mean it happens in year 32. What this means is it happens 32.7 years after 1990, which means that the year it actually happens in is 2022. So hopefully, these memories of the exponential growth model have been coming back. You don't necessarily have to use a lot of calculus for these problems. You just have to be able to recognize so that you can convert between the differential model and the regular function. If you have questions on anything from Chapter 9 or earlier that you're going to see on the quiz tomorrow, please let me know, and I'm happy to help. Welcome to semester